Hi, welcome to a brand new episode on generative AI. My name is Satyajit Pattnaik and I welcome you back to my channel. In case you are a complete beginner in generative AI, I already have a 6 hours dedicated video on generative AI for you to get started with. Now in this video, we shall be focusing on the next steps, which is fine tuning. We will be focusing on LoRa and QLoRa in this video, which means low rank adaptation and quantized low rank adaptation. Now, this is a very complicated topic, so I would request you to get through this video end to end, properly understand, because I have made sure that my explanations are going to definitely help you out, and this video can be your one-stop solution. I'm pretty much sure that you will be able to understand the entire concepts behind LoRa and QLoRa by the time you finish this video. So before getting started, I also wanted to let you know that in case you like this video, appreciate if you can leave a comment and like this video and subscribe the channel. On top of that, I'm also working on multiple projects. If you want me to come up with a dedicated project on data analytics or focused on Power BI or machine learning, NLP, deep learning or generative AI, let me know in the comment section and I will prioritize based on the number of comments. See you in the video. I hope you enjoyed this video. Hi, let's try to deep dive into LoRa. What is LoRa? LoRa is low rank adaptation. Now, if I have to divide it, LoRa is consisting of two different parts. One being, let me just close it, one being the low rank part, and A basically means the adapters. Now, if I have to divide it into multiple phases, let's try to write it this way. The phase 1, we can focus more on what low rank is. Phase 2, we can look at what adapters are. And phase 3, we will look at the combination of LoRa and adapters. Now let's try to take example and try to understand more about the phase 1 part. Now what is phase 1? Phase 1 is all about low rank. What do you mean by a rank? So let's write it down. What is rank of a matrix? If you just don't know, in simple terms, rank of a matrix is nothing but the number of linearly independent rows or columns. So let's say we have a matrix. Let's say we have a 10 cross 10 matrix, right? How many linearly independent rows or columns do we have? Let's try to take an example to understand about the rank part. I'm taking an example where I will be focusing more on the columns part. Okay, so let's consider column for simplicity right now. Let's take an example. Example 1. Let's say I'm going to write it down. Let's say my numbers are 1, 2, 5, 3, 4. Let me write it properly. 3, 3, 9, 6, 9. 2, 3, 8, 5, 7. 4, 1, 6, 5, 9. Just for simplicity. Now, this is a 4 cross 5 matrix, right? So, let me just draw it in a different color. How many columns do we have? Column 1, column 2, column 3, column 4, and column 5. And rows, there are 1 row, 2 row, 3 row, and 4 rows. So there are 4 rows and 5 columns. Our task for this exercise is going to be identify the rank. Now going back to the basics, what is rank? Rank is nothing but the number of linearly independent rows or columns, right? Now let's first talk about, before getting into this matrix, what do you mean by linearly dependent or linearly independent? Now linearly dependent simply means, let's say I'm talking about few numbers, let's say 1, 2, 8. Let's say this is a list A, and there is another list which is 2, 4, 16, or there is another list which is 5, 7, 9, and let's say there is another list D, which is, let's say, 1.4, 2.8, and let's say 1.4 times 8, 11.2. Now in this case, let's try to understand what is linearly dependent or not. List B is nothing but 2x of list A, right? So can I write it this way? List B is nothing but 2 multiplied with list A. I can. Can I write list C as something like this? No. So C is not linearly dependent. Talking about D, D is nothing but 1.4 times list of A, right? And that's why list D is also linearly dependent. So how many linearly independent lists do we have out of these 4? Eventually 1. Now let's talk about this particular matrix. Okay, for simplicity, let me just copy this. Okay, I have copied. So let me just go a little bit down, and we'll try to focus only on this example, right? Now in this example, our target is to identify what is the rank. Now, and I'm just considering column by column. I'm not complicating it, not going into the rows part. Let's try to focus on columns. C1. For C1, do we have any previous column based on which C1 can be dependent or independent on? As C1 is the first column, C1 is purely independent by itself. Okay, so I'm just circling it because this is linearly independent. Now talking about C2, is C2 somehow linearly independent or dependent on the previous column? Now this element is like twice of this element, but this element and this element are same. This element and this element are like 1.5 times, and this element and this element are like reduced by 75%, right? Or reduced by it's like 1/4, right? So C2 is also not dependent linearly. Now I'll talk about C3. Is C3 dependent on either C1 or C2 or both? Can I write C2 as, the first one is nothing but something like C1 plus 2C2? For first element, yes. For second element, 3 plus 2C2, which is 3 plus 6, 9, yes. C1, 2 plus 6, 8, yes. 4 plus 2, 6, yes. So this particular formula is valid. Sorry, this is not C2, this is C3. Okay, this formula is valid for C3, right? Okay, that means C3 is not linearly independent, rather it is dependent on both of these columns. So C3 is not linearly dependent. What about C4? Can we have a formula? Is C4 linearly dependent on either of these columns, C1, C2, C3, or maybe a combination of that? So if you look at C4, it's purely C1 plus C2, right? 3, 1 plus 2, 6, 3 plus 3, 5 is 2 plus 3, 5 is 4 plus 1. What about C5? So C4 is also no. What about C5? C5 is pretty much, it's like 2C1 plus C2. Now we can validate that. 4 is 2 plus 2, 4, 6 plus 3, 9, 4 plus 3, 7, 8 plus 1, 9. Yeah, this holds true, right? So either of these columns, C3, C4 and C5, are not linearly independent. They have a linear dependence on C1 and C2. Now here we have how many linearly independent columns? We have C1 and C2. So what will be the rank? The rank will be 2. So you can write rank as R. R is going to be 2. Now, so mathematically, I can write down these as C1 is dash C1 plus dash C2, C2 as dash C1 plus dash C2, C3 is dash C1 plus dash C2, C4 is dash C1 plus dash C2, C5 is dash C1 plus dash C2. So C1 is 1 C1 plus 0 C2, C2 is 0 C1 plus 1 C2, C3 is 1 C1 plus 2 C2, C4 is 1 1, and C5 is 2 1. That's my final equation. Moving on, the reason why I did this was, if I know this, if I know the linear dependence of all of these columns with respect to their previous columns, can I write it this way? This 4 cross 5 matrix can also be written down as, let me just write it, 1 2 3 3 2 3 4 1 multiplied with 1 0 1 1 2 0 1 2 1 1. If you look at closely, this is nothing but a 4 cross 2 matrix. This is a 2 cross 5 matrix. Now going back to very basic mathematics, when you are doing a matrix multiplication, let's say you are doing m cross k cross k cross n, this basically becomes m cross n, right? That's the basic fundamentals. So the output of this is going to be a 4 cross 5 matrix. So what I have done here is, this is nothing but my C1 and C2. These are nothing but my independent columns, and these are all of these numbers. The first row is 1 0 1 1 2, the second row is 1 0 1 2 1 1. Okay, now if you start doing the matrix multiplication, let me just quickly write down the formula of matrix multiplication. Is Cij is nothing but, let's say, summation of k is equals to 1 to m. I will write it down as aik multiplied with bkj. Now here a is my first matrix and b is my second matrix. Okay, that's my formula. Now let's try to go and try to solve this matrix multiplication. Not going to solve it for the entire thing, but let's try to solve it for row number 1. For row number 1, let's say my C11 is going to be, now this C, don't get confused with this C and that C, okay? Now this top C is for column. Now this C is basically coming from this formula. Now this is nothing but your new matrix. A is your matrix 1, B is your matrix 2, and C is your matrix 3, which is the multiplication of M1 cross M2, right? So in this matrix C, the first row and the first column, this is what the meaning of C11 is. It's nothing but this multiplied with this. So 1 multiplied with 1 plus 2 multiplied with 0, which is 1. C1 2 is going to be this multiplied with this. 1 multiplied with 0, 2 multiplied with 1, which is 2. C1 3 is going to be 1 multiplied with 1, 2 multiplied with 2, which is going to be 5. C14 is going to be 1 multiplied with 1 plus 2 multiplied with 1, which is going to be 3. And C15 is going to be 1 multiplied with 2 plus 1, plus 2 multiplied with 1, which is 2, 2, 4. 1, 2, 5, 3, 4. Going back to the first matrix. I'm just copying this here so that we are on the same page. Right? Do we have the first row? Yes. Do we have the first row? 1, 2, 5, 3, 4. Moving on. Moving on to row number 2. So C21 is nothing but this multiplied with this. 3 cross 1 is 3. 3 cross 0 is 0, which is 3. 2 is 3 cross 0 is 0 plus 3 cross 1 is 3, which is 3. C23 is 3 cross 1 is 3, 3 cross 2 is 6, which is 9. C24, 3 cross 1 is 3, 3 cross 1 is 3, which is 6. 25, 3 cross 2 is 6, 3 cross 1 is 3, which is 9. 3, 3, 9, 6, 9. 3, 3, 9, 6, 9. Did we get this? Yes. Not going to do it for all the rows. I'm skipping row number 3. You can do that as part of your exercise. So let's say 4, 1, 4, 2, 4, 3, 4, 4, and 4, 5. 4, 1 is going to be nothing but just doing it in a different color so that it is visible to us properly. 4, this. 4 with 1 is 4 and then 0. So 4. 4 with 0 is 0. 1 with 1 is 1. So 1. 4 with 1 is 4 plus 2 is 6. 4 with 1 is 4 plus 1 is 5. And 4 plus 2, 4 multiplied with 2 is 8 plus 1, 9. So this is going to be 4, 1, 6, 5, 9. So eventually what I'm trying to say is this particular matrix, which was a 4 cross 5 matrix consisting of 5 different columns and 4 different rows, do not actually need information about all of these 3 columns. We are able to get this final output just by using C1 and C2, and that is because C1 and C2 are linearly independent. C3, C4, C5 somehow has a linear dependence with C1 and C2, right? So that's why we are able to write it this way. So going back, our initial matrix was something like this: 1, 2, 5, 3, 4, 3, 3, 9, 6, 9, 2, 3, 8, 5, 7, 4, 1, 6, 5, 9. Now this was a 4 cross 5. We were able to write it like this, right? So the first 2 columns are this, which is a 4 cross 2 multiplied with 1, 0, 1, 1, 2, 0, 1, 2, 1, 1, right? Which is 2 cross 5. So with respect to the rank, this becomes your rank. Understood? Clarity? Now, what is the advantage? The advantage is if this is your original neural networks, if you do a full forward pass and a backward propagation, you are changing 20 parameters or 20 weights. But with simple changes with respect to low rank, you're able to get it with how many? 4 cross 8, 4 cross 2 is 8, and 2 cross 5 is 10, and the combination of them is going to be 18 parameters. And that is the example of parameter efficient fine tuning. You do not need to change all the 20 parameters, you can only change 18 parameters, and that is all about low rank. And this is just an example, right? I could have taken a difficult example, but it is difficult to understand. So I think this is clear to everybody. And 18 parameters, of course, is smaller than 20. That means we are storing less parameters, right? So generally speaking, the formula looks like this. W, which is D cross K, is nothing but A, which is D cross R, multiplied with B, which is R cross K. That becomes this matrix. Hi, welcome back. Let's move on to the next part, which is phase 2 adapters. Now, to begin talking about adapters, let me just give you a brief recap that usually there are three type of models, right? To get started with, let's have model 1, and then we have 2, and then we have 3, right? See, the difference between all of these three is very simple. The first one is nothing but a untrained model, right? It's not trained, so I'll just write it down as untrained model. The second model is trained with trillions and trillions of data, right? And this is nothing but a pre-trained model. I'm writing down as PT. And eventually, for your own custom data, here also we have input, here also we have output, here also we have input, and here also we have an output, right? And let's say you're training this on custom data, that becomes fine-tuned model. Now, what is the problem with a fine-tuned model? What are the cons of fine-tuned model? So if I start writing down the cons of fine-tuned model, we just are time consuming and expensive process as LLMs get bigger. I'm not explicitly talking about LLMs, but in general, transformer models, right? As transformer models or LLM becomes bigger. The second is catastrophic forgetting issue. Apart from forgetting issue, we also have an overfitting problem as model forgets pre-trained objectives. Because when you are going to use an existing model, imagine a simple example, okay? I'm not talking about large language models. Let's try to talk about a very simple deep learning model example. Let's say I'm talking about Inception v4, right? Now, I'm not sure how many classes this model is trained on. Again, I'm taking an example, so try to understand the idea, right? Imagine Inception v4 is pre-trained with trillions of images and it has 1,000 classes, right? And if you are going to use this as one of your initial layers for your very specific use case, let's say you are trying to do some x-ray detection or something like that, or you are just analyzing, let's say, solar panel images for your use case. Some of the solar panels have cracks, some of them have no cracks. So you have two different use cases: solar panel with cracks and solar panel without cracks, right? Now this is a very typical use case, right? You have your own classes, and these classes might not be present inside this, right? That means when you're trying to use it as a pre-trained model and you're doing a fine tuning, that means you're updating all the weights, right? In that process there can be a scenario where the model might lose information. So there are scenarios where the model will start forgetting and will start overfitting. Could be a scenario, right? So let's say we need to fine tune a model. Let's say we'll take an example here with respect to natural language processing. Let's say we're going to talk about BERT. Okay, so everybody should know about BERT. BERT is nothing but bidirectional bidirectional encoder only representation of transformers, right? And BERT has different variants. I'm just taking an example of, let's say, BERT large. Okay, now BERT large has 24 transformer blocks, right? And how does a BERT model looks like? If you have input coming in from here, let's say I'm going to draw something here, let's say, right? And let's say this is going to be my output, right? Now inside this, let's say I'm going to draw it in red blocks. This is one transformer block. Let me draw here another transformer block, dot 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 dot, another transformer layer here, right? So this is your block 1, block 2, and block 24. And what's inside these blocks? Let's say you have one, sorry, you have multiple blocks. Now this is, let's say, your I'll just talk about, let's say this is your multi-head attention, and let's say here is your feed forward layer, and then we have your layer normalization, and then you're passing the information. Okay, so let's say I'm just writing it down. The first one is nothing but your multi-head attention. Okay, the second one is basically your feed forward layers, and then the third one is basically your layer normalization. Okay, and if I have to point it out, this is this, this is this, and this is this, right? And the same architecture remains for rest of the blocks, right? These are the 24 blocks that we have now. And this is a very generic BERT large model, right? And BERT large model usually have around 345 million parameters. That means for the entire retraining with full parameters, you will be needing 344 million parameters weight changes, right? So without BERT, I mean, without PEFT, if you are doing a full parameter training, then you need definitely 345 million weights changes, right? In the entire forward pass and the backward propagation, right? So, what is the problem here? What is the problem if we store or change 345 million parameters? Time consuming, memory consuming, and a lot of issues, right? Latency issues. So, how can we perform a low rank adaptation here, or in simple terms, how can we perform adaptation, sorry, adaptation, not adaptation, adaptation, right? How can we use adapters? Because this is what we're talking about in this scenario, right? This is the phase 2, and we need to talk about what adapters are. So BERT large model is basically of 345 million parameters, right? Now 345 million parameters basically means if you have your neural networks, let's say you have your input and you have your neural network, something like this, basically in your forward pass and your backward propagation, 345 million weights will be changed, right? And for this we need to store 345 million extra parameters for every forward pass or backward propagation, and that is where the adapters will come into picture. that is where PEFT will come into picture. We talked about PEFT, which is parameter efficient fine tuning, right? Now, what exactly is parameter efficient fine tuning? I'm going to use the same BERT model but with adapters. And what does that mean? That means I'm going to do a very small change in this architecture. After multi-head attention and feed forward layers, I will quickly add a adapter. So I'm just rubbing this off. Here, as this is a new thing, I'm just writing down in, let's say, purple. So I'm going to add an adapter here, same adapter here, and same adapter here, right? So these are all nothing but my adapters, right? And adapters are added serially in all the transformer blocks, right? Now adapters helps adapt to a fine-tuned task. Okay, so taking an example, we have BERT, which is trained on multi, let's say, what are BERT models trained on? BERT models are trained on, let's say, masked language modeling plus next sentence prediction, right? Now, your BERT models is already trained on mask modeling, mask language modeling, and next sentence prediction. And imagine you want to do a very specific use case, you want to do something on sentiment analysis. Sentiment analysis. And you want to train your own model, own data, and you want to do some parameter fine tuning, right? So here, as we are adding adapters, right, what's going to happen is only adapters weights are going to be updated. Your entire transformer block will not be updated, only the adapters weights. What does that mean? That basically means, let's say we want to do some fine tuning use case around sentiment analysis, and we have our new set of Q&A, right? And our new architecture will look like this, where we have adapters in all of these transformer blocks, right? Which basically also means that only adapter weights are going to be updated. Only adapter weights are updated, other weights are frozen. Okay, and it also means only a fraction of weights, not total 345 million weights. Only a fraction of weights are going to be updated, and eventually it's going to be less memory consumption, less CPU utilization, and it's basically what we call as PEFT, and that's basically the adapter part. So we are clear on the low rank part and we are clear on the adapter part. Now let's try to combine, and let's try to also see what LoRa means, because LoRa is low rank adaptation. That means the combination of low rank and adapters. Now what I explained right now is just the functionality of adapters, right? We still need to understand what is the difference between this traditional adapters technique and LoRa in the next video. Hi, welcome back. In this video, we shall be focusing on the phase 3, which is LoRa, which is low rank adaptation. Now, we already have a fair amount of idea about what low ranks are. In short, when we are working on a matrix, let's say D cross K, we will be eventually be using, let's say, D cross R multiplied with B R cross K. And this is basically your rank, right? And what is a rank? It's already mentioned here, number of linearly independent rows or columns, right? And in the previous video, in the phase 2, we also talked about what adapters are, right? Adapters are nothing but introduced in, okay, before talking about that, quickly let me just show you what this is, right? This is nothing but your transformer block, right? for an example, you can treat it as a BERT24 model, which is a BERT large model, right? Now this is your BERT1, this is your BERT2, dot dot dot, this is your BERT24, and each of your transformer block has a multi-head attention, has a feed forward network or a layer, and then we have adapters. Now these adapters basically help you to cut down the number of parameters to a smaller parameters, right? And how does it do? Initially BERT24 is nothing but a 345 million parameter model, right? Without adapters, what happens is when you're going for a forward pass and a backward propagation, you need to update all of these weights. When you're introducing adapters have their own parameters. Let's say each adapter here is having like a 1 million parameters for an example, right? Let's say I'm talking about 1 million parameters. So how many total parameters do we have? We will be having 24 million parameters, and in this case we don't have to train the full network or the full BERT24 model. We just need to retrain, or we just need to use the adapter weights, and only the adapter weights will be trained. Now what is the drawback of phase 2 when we are just using adapters versus low rank adapters? Low rank adapters is nothing but a combination of phase 1 and phase 2, right? With just adapters we are still cutting down from 345 million to 24 million, which is completely fine. But low rank adaptation or low rank adapters further helps you to go down, right? The drawbacks of this process is adapters are good, but they are also having increasing latency and inference time, because adapters are basically added serially, right? Now let's try to combine both of our learnings that we understood in low rank and adapters. Let's try to understand what LoRa is. Okay, so let's say we are talking about BERT model, right? BERT large model is nothing but 345 million parameters, right? Now let's try to talk about three different scenarios, right? First will be without anything, without any adapters or without any low ranking technique. The total parameters are going to be 345, right? So let me just write it down here. Okay, before writing it down, let me just erase a little bit so that we have some space here. Okay, we have some space here. I'm just also deleting these things because these things we already know. And here let me just write it down. Let's say we have 1 million parameters. It's going to be 1 million cross 24, which is 24 million parameters. Okay, now let's talk about three scenarios, right? Scenario 1. Scenario 1 is nothing but without adapters. Now without adapters, what's going to happen is total parameters is going to be 345 million, right? Now during back propagation, when you're doing a forward pass and a back propagation, all of your 345 million parameters are going to be updated. All 345 million parameters are updated. This means every weight in the model is adjusted based on the gradients calculated during the back propagation step. Okay, now talking about scenario 2. Scenario 2 is with adapters, with traditional adapters. Okay, with traditional adapters, what's going to happen is instead of total parameters, I'm just going to write it down as adapter parameters, because here we don't care about how many total parameters do we have, because we just care about adapter parameters, because adapters are added to each of these transformer blocks, right? Now let's say we add an adapter module to each of the 24 transformer blocks, and let's say each adapter consists of let's say a couple of layers, right? A feed forward layer, for example. So let's say if each adapter has, for example, let's say 1 million parameters, each adapter has 1 million parameters. In that case, um, the total adapter parameters is going to be around total adapter parameters are going to be around 24 million with like 24 transformer blocks multiplied with 1 million, right? Now during back propagation, how many parameters are going to be updated? Only 24 million parameters of the adapters will be updated, while the original, the scenario 1 was having 345 million parameters, right? So obviously it's helpful. Now low rank adaptation is even better than this, or just change it to scenario 2, change it to scenario 3, right? Scenario 3 is with LoRa. LoRa is a combination of adapters plus low rank system. No, low rank basically means cutting down your original neural networks into a low rank neural networks, where we need to identify the number of linearly independent rows or columns, right? All the dependency will be removed, right? So let's say here I will write it down as low rank matrices. Now let's say instead of adding a full adapter, LoRa introduces two low rank matrices for each transformer blocks. Let's say, for example, LoRa introduces two low rank matrices in each transformer block, right? Now how many parameters we will have? So let's say parameter count, let's say, now again depends on the rank, right? For example, if we have a rank of 8, let's say, for the low rank matrices, let's say each matrix has dimensions that allow for efficient representation. The total parameters might look something like, I would say, let's say we have around 0.5 million parameters for each low rank matrices. Then the total LoRa parameters is going to be around, so it's going to be 0.5 million multiplied with the 24 blocks that we have. The total is going to be 12 million parameters. The total LoRa parameters or total updated parameters is going to be 12 million. Now during back propagation, only 12 million parameters of the adapters will be updated. Now imagine it to be a even low rank, not even 8, let's say 2 or 1. So the number of trainable parameters are even going to decrease from there. I hope you are able to understand, right? So if you talk about the summary, without adapters we were having 345 million trainable parameters. With adapters we have only 24 million parameters, and with LoRa we have 12 million parameter updates, right? So the conclusion here is, using traditional adapters we are able to significantly reduce the number of updated parameters, but LoRa takes it a step further by using the low rank approximations, resulting in even fewer parameters needing to be updated while still allowing the model to adapt effectively. This makes LoRa a very efficient method for the fine tuning technique. So I hope you understood what LoRa means. Hi, welcome back. In this video, we will be talking about our next thing, which is QLoRA. We already know what LoRa is, which is low rank adapters. The Q part here is nothing but quantized. And what do you mean by quantization? I think we have already understood quantization in a separate video, that quantization is nothing but reducing the precision of numerical values, typically the floating point values representing the weights and possibly other parameters in the model, to a lower bit representation, right? So let's say we are talking about a large language model. A large language model is usually trained on billions of parameters, right? I'm just writing it down as X billion parameters. For example, if you're talking about Tiny Llama has around 1.1 billion parameters. And all of these parameters are nothing but represented by floating point values, right? And when we drop it down to a lower precision, that means either to a 16-bit floating point. So by default, it's a 32-bit floating point, right? I hope everybody knows about this thing. If you break it down, you can either, so each, so if I have to write it this way, 32-bit is eventually nothing but 4 bytes, and 1 byte is 8-bit, right? So 1 byte is nothing but 8 bits. So if you have to divide this 32 bits, you can either write 8 bits each, or you can just write down 1 byte, 1 byte, 1 byte, 1 byte, right? So if you have to break it down, you can either go to a 16-bit, which is nothing but 2 bytes, or you can go further down to 8 bits, or you can go to further down to 4 bits, or you go to further down 2 bits, right? So there are different quantization techniques, right? So eventually quantization is nothing but reducing the precision of numerical values. And if you remember, we have also gone through the different precision types, right? For example, talking about 32-bit. 32-bit is nothing but, you can consider it as FP32, right? Floating point 32, which is nothing but your 100% default model. Accuracy is best, computation power is very high, right? Computation cost is very high. 16-bit is nothing but a 50% reduced model. It's like a good model, good balance between the accuracy and speed. 8-bit is like a 25% model of the original one. Accuracy will be little bit lesser, but speed gain will be massive. 4-bit is again less accuracy, very fast, and 2-bit is insanely fast, but definitely very bad at accuracy. But nevertheless, these models also exist, especially in your IoT sensors or edge devices. So we use this, right? So that's basically quantization. If you don't know, please go back to the quantization videos and you should be able to understand what quantization is. Now coming back to QLoRA. What is the quantized LoRa? So we will try to go back to the previous screen where we had done different scenarios. I hope everybody remembers all of the scenarios. What we will be doing is we will be creating a scenario 4. Sorry, my bad. So we will be creating a scenario 4, which eventually is nothing but, well, let me just see, long press to unlock. Okay, let me just delete it and create it again. I think it's unlock. Okay, so the fourth scenario is with QLoRA. Now what is the difference between, so we all know these three scenarios, right? What is the difference between LoRa and QLoRA? Let's try to understand that. Now see, trainable parameters wise, there is not much of difference, right? In the original one, without the adapters, we were using a BERT as an example, BERT large model, where we were using 348 parameters, 345 million parameters, right? And similarly, we started talking about adapters. So with traditional adapters, we assumed that each adapter has 1 million parameters, and we were able to get 24 million trainable parameters. And in LoRa, assuming like a 0.5 million parameters with a rank of 8, we were able to achieve 12 million trainable parameters. Now what is quantized LoRa? So quantized LoRa, or basically QLoRA, is nothing but an extension of LoRa that introduces the quantization technique to further enhance the efficiency in fine tuning of a particular model. Let's say in this example, we are taking the example of BERT large. So it will be even a better version of that model using the quantization technique. Now, parameters wise, nothing will change. Quantization basically refers to the reduction of the precision of the model weights, typically which is a 32-bit floating point, to a lower bit representation like 8-bit, 16-bit, 4-bit or 2 bits, right? Now this reduces memory usage and improves computational efficiency. So in QLoRa, both the original weights, the original model weights and the low rank matrices are quantized, right? So so parameters wise, nothing really changes. In your traditional in your LoRa also we were having 12 million parameters. In QLoRa also we will be having same amount of parameters. So let me just write it down. Everything will remain the same. QLoRa introduces, okay, so it's same, it's just the same, it's the same 12 million parameters, but the weights are reduced precision, as simple as that, right? So that's basically the difference between LoRa and QLoRa. Apart from that, the core concept behind both are same. Both uses a combination of low rank and adaptation, but LoRa is on full precision. So when we were talking about the different precisions, right, let me just go back to that particular table. If I have, yeah, this one. So in simple terms, this by default is LoRa, and if you use any of them, that's basically QLoRa. That's it. Trainable parameters, no impact, but within those parameters, QLoRa is a better version of LoRa, right? Because the because of the lower precision rate. That's it. The memory consumption is lower and accuracy is better. The performance is better. So that's all about QLoRa and LoRa.